So our next way that we can improve our approximation for the area, in fact, get an exact approximation for area, is to generalize the idea of this summation. So right now we have the idea that the area is approximately equal to the sum from I equals 1 to n of f of x sub I delta x, where n is the number of rectangles. So if instead of specifying n equals 8 or n equals 10 or n equals 10 million or anything, what if I were able to come up with an expression that represented the sum and then use a tool that we developed much earlier, the limit as n approaches infinity? So if I could do that, then I could effectively put infinitely many rectangles under the curve. All right, so the first thing, we are going to do that. That's exactly what we're going to do. All right, in order to do it, the first thing we need is a connection between sums of this nature and things that we can take limits of as n approaches infinity. All right, you can take limits as n approaches infinity of rational expressions like these, like n times n plus 1 over 2, n times n plus 1 over 2 times 2n plus 1 over 6. These are only parts of what we're going to develop for this sum. You can see if I did limit as n approaches infinity of any of these things, they would all just be infinity. Okay, so this is only a part of the sum that we're headed to, but it's our starting point. So what we're going to do is we're going to look at correspondence between this sum and this expression, this sum and this expression. There's really only two sums in their expressions. I just have sort of a different layout for these. All right, so we're going to start by saying, okay, how does this expression relate to this sum? So what do we mean by the sum from I equals 1 to 3 of I, right? So we're going to use n equals 3 in this sum. It means we're going to do I equals 1 to 3 of I. So if you're not familiar with the summation notation, you know, this is how it works. If you're still confused, send me an email. We'll talk about it in Flex. The sum from I equals 1 to 3 of I just means 1 plus 2 plus 3, which is 6. All right, and then if I put n equals 3 in this expression, I'm going to get 3 times 3 plus 1 over 2, which is 12 over 2, which is also 6. So we're going to expect these to come out the same, but don't assume that they're going to be the same. I want you to calculate each of these separately. And I'm going to try and develop that thereby a set of examples to convince you that they're probably the same. Now that's not the same as a proof. Now, by the way, on the back of this sheet is the ways that you prove these formulas. You absolutely do not have to do what is on the back of the sheet. On the back of the sheet is something I wrote up a few years ago for a student who really needed some extra challenges every single day, and I gave him this to work through on his own. Okay, so you do not have to do this, but by the way, what we're doing over here is not a proof of the equality of these things. It's only a suggestion that they're equal. These back here are the proofs. So if you are interested in that and you want to pursue it with me, I'd be happy to pursue it with you. However, I recommend you've probably got other things on your plate right now, and you could take these on faith for now. And in a more advanced class, you can prove them. All right, so here's the first example. So, you know, basically do that with each of these. You know, what's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, all right? So I want you to fill out this chart. In fact, you're going to turn this chart in completely filled out, and showing that you calculated this according to this formula, and you calculated this according to this formula. So for this one, I have sum from I equals 1 to 3 of I squared, so that means 1 squared plus 2 squared plus 3 squared. That's 1 plus 4 plus 9. That's 14. All right, so if I plug in n equals 3 here, I get 3 times 3 plus 1 times 6 plus 1 over 6. All right, so I can reduce the various things here, right? That's 3 times 4 times 7 over 6. 3 times 4 is 12. 12 divided by 6 is 2. 2 times 7 is 14. So lo and behold, they're the same again. Okay, so I want you to start by just filling out these two, and fill these out on your own, and then take a pause and come back, and then I'll show you a couple of nifty things about it. Okay, so I'm assuming you've filled out the rest of this, so I want to show you a couple of things. So one is, when we're doing the n equals 7 for this one, all right, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. So I'm going to show you a trick that is credited to Carl Gauss. He might not be the original inventor, but he's credited with it. 1 plus 7 is 8. 2 plus 6 is 8. 3 plus 5 is 8. I have 3 8s and a 4. That's This doesn't seem right. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. How come I got 42 when I did that before? Maybe it's not. 8 plus 8 is 16, plus 8 is 24, plus 4 more is 28, right? So you can basically combine pairs that add up to certain things. I had a different result before, but that just goes to show that I should not prep my classes. It only causes grief and headaches. Let's just verify that since I'm suspicious of that one. 7 times 7 plus 1 over 2 is the same as, get out of here, cat, 7 times 8 over 2. So that's 7 times 4, which is 28. All right, so yeah, that was right. Okay, so when I do up the 10, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. So here the Gauss trick really pays off, right? 1 plus 10 is 11. 2 plus 9 is 11. 3 plus 8 is 11. 4 plus 7 is 11. 5 plus 6 is 11. How many 11s have I got? I got 5 of them, so it's 55. Ultimately, this method of counting is where this formula comes from. You can think about that if you want. All right, so then when I plug into this formula, of course, I get 10 times 10 plus 1 over 2, which is the same as 5 times 11, which is 55. All right, so on these ones with the squares, there's not a nifty trick like that, but I did notice some kind of interesting patterns when I did the 7 one. So I have 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. All right, so that gives me 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49. So here's what I noticed that was interesting about that. 49 plus 1 is 50. 36 plus 4 is 40. And then it doesn't get that much easier from there, but 25 plus 16 is 41, but then plus 9 is 50, right? So you really have 50 plus 40 plus 50. So that's 140. So it's 140 over here. All right, and then when we put this over here, we're going to do, there's some interesting simplifications over here. So we have 7 times 8 times 15, right? And it's over 6. So if I remember that I can reduce, the 6 and the 15 to 2 and 3, because everything's multiplied, 2 and 5, I mean. And then I can reduce the 2 with the 8 and have 4. So now I just have 7 times 4 times 5. 20 times 7 is 140. So there are some sort of reducing tricks. I don't think you're going to find anything quite so nifty in 10, although what you can do is take your 140 and then just add 8 squared plus 9 squared plus 10 squared, and it's going to simplify your work. All right, now let me jump down to part 2 where it's calculator permitted, not calculator permitted, calculator permitted. I'm going to show you some nifty things that you might not have known your calculator can do. And you do need to have the most updated version of the operating system for this. If what I'm showing you doesn't exist, go to that little port on the back, hook it up to your computer, go to ti.com and download the most recent operating system. If you have a TI-83, you're out of luck and you have to do these by hand. All right, but now let me show you. Well, you could probably do it with what you call it, like Wolfram Alpha or some other computer program. All right, so this was calculator permitted. See, these are all no calculator. That's why I worked them all out by hand. Right, it says no calculator, so I hope you didn't use one. All right, this one's calculator permitted, because I'm not going to sit here and add up 50 perfect squares. I'm not going to do that. So here's what your calculator can do that is so awesome. Math. Look what's down here. Look what's hiding down here. Summation. Yeah. So I can use whatever variable I want. I can use x, or I could use I or n. It's just easiest to use x because that is right there. X equals 1. I just copy exactly how this is. We're going up to 50, and it is of I squared, so I put in x squared, and I just hit enter, and voila, it's 42,925. All right, 42,925. Okay, this formula, it probably would be worthwhile, since you're going to use it, 3 times, maybe 4 times, I guess. Probably be worthwhile to put that in your y1. So we'll go over to our y1, and I'll just clear that, and we'll put in x times x plus 1 times 2x plus 1 divided by 6. All right, that's going to be my y1. So now I will go y1, so vars, y vars, enter, y1 of 50. Boom, it's 42,925. Okay, so you need to calculate these by using the calculator. Was I going to say something else about that? I don't think so. I guess the goal is I want to establish these two summation formulas, which we are going to use when we do the infinite sum. So our two summation formulas that we're going to end up with here are that the sum from I equals 1 to n of I is equal to n times n plus 1 over 2, and the sum from I equals 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 over 6. A couple of strange results. You do not have to memorize these or even know that these formulas exist, but we're going to use them in order to take these types of sums, write them as expressions involving n, and then take a limit as n approaches infinity. Your job is to complete this sheet and convince yourself, become convinced that these two formulas are true. And if you're not convinced by this handful of examples, you could possibly be convinced by these crazy proofs. And if you don't want to convince yourself by that, you can just take my word for it. It's true. All right, so that's all we're going to do on this for now. And next week, we're going to apply the power of the limit to these expressions involving sums.